Settle into the Sleepy Mind channel. Tonight, we explore constellations. These patterns of stars have guided human understanding of the night sky for thousands of years, shaping how we organize the heavens and interpret what we see above us. If you enjoy stories like these, feel free to like and subscribe, as more videos are posted weekly. Let us begin. When we look up at the night sky, the stars appear scattered across a vast, dark background, forming patterns that feel both random and familiar. These patterns are what we call constellations. However, it is important to understand that a constellation is not a physical grouping of stars in space. The stars that appear connected in the sky are often separated by enormous distances, sometimes hundreds or even thousands of light years apart. From our viewpoint on Earth, they simply line up in ways that create recognizable shapes. As a result, constellations exist as visual patterns rather than real structures. They are the result of human perception, where the mind connects points of light into meaningful figures. Early observers looked at the brightest stars and began linking them together, creating shapes that resembled animals, people, or objects. These shapes became a way to organize the sky, turning a complex field of stars into something that could be remembered and shared. Over time, these patterns were refined and standardized. The night sky was eventually divided into 88 constellations, each covering a specific region. Together, these constellations form a complete map of the celestial sphere, ensuring that every point in the sky belongs to one defined area. This system allows astronomers to locate objects precisely, using constellation names as a reference. Although the stars within a constellation may appear close together, their true positions in space reveal a very different picture. Some stars are relatively nearby, while others lie far beyond, their light taking thousands of years to reach us. The patterns we see are therefore a coincidence of perspective. If we could view the same stars from a different location in the galaxy, the shapes would appear completely different, breaking apart into new arrangements that no longer resemble familiar figures. This idea highlights the role of observation in shaping our understanding of the universe. Constellations are not fixed objects, but interpretations created from a specific point of view. They represent a way of organizing information rather than a reflection of physical structure. By recognizing this, we begin to see the sky not just as a collection of stars, but as a system shaped by both nature and human perception. The concept of dividing the sky into regions became essential as astronomy developed. Without a structured system, it would be difficult to describe where a star or object is located. By assigning each part of the sky to a constellation, astronomers created a framework that allows for clear communication and precise mapping. This system remains in use today, forming the foundation of modern star charts and observations. The standardization of constellations was formalized in the early 20th century when the International Astronomical Union established official boundaries for each constellation. These boundaries function like borders on a map, defining where one region ends and another begins. Once these divisions were set, every star in the sky was assigned to a specific constellation, ensuring complete coverage without gaps or overlap. This mapping system provides stability, even as the stars themselves slowly move over time. Stars are not fixed in place. They travel through the galaxy, changing position gradually over millions of years. This movement, known as proper motion, means that the shapes of constellations are not permanent. Over long periods, the familiar patterns will shift and distort, eventually becoming unrecognizable. Despite this gradual change, the boundaries of constellations remain fixed from our perspective. The map stays the same, even as the stars within it move. This creates a stable reference system that can be used across generations, allowing astronomers to track objects and record observations without confusion. The constellations act as a framework that holds the sky together in a consistent way. Looking further back in time, we find that the origins of constellations are deeply connected to human culture and storytelling. Many of the constellations we recognize today were named by ancient civilizations, particularly those of Greece and Babylon. These early observers saw figures in the stars and attached stories to them, turning the night sky into a vast collection of myths and legends. In Greek tradition, constellations often represent gods, heroes, and creatures from mythology. These stories were passed down through generations, preserving both cultural beliefs and knowledge of the stars. The constellation Orion, for example, represents a hunter, while others depict animals or mythological beings. These figures provided a way to remember the positions of stars and navigate the sky. However, Greek constellations were not the only interpretations. Other cultures around the world developed their own systems, seeing different patterns in the same stars. Chinese astronomers divided the sky into smaller groups known as asterisms, each with its own meaning and significance. Polynesian navigators used star patterns as a guide for ocean travel, relying on their knowledge of the sky to move across vast distances. This diversity of interpretation shows that constellations are not universal in their meaning, but are shaped by the cultures that observe them. The same group of stars can represent different figures depending on who is looking. This reinforces the idea that constellations are a human creation, built from observation and imagination, rather than physical connection. Beyond storytelling, constellations played a practical role in everyday life. Ancient societies used the movement of stars to track time and mark the seasons. The appearance of certain constellations in the night sky signaled changes in weather and guided agricultural activity. Farmers learned to associate specific star patterns with planting and harvesting cycles, using the sky as a natural calendar. Before the development of clocks and written calendars, this system provided a reliable way to measure time. The regular motion of stars across the sky created patterns that could be observed and predicted. By watching when certain constellations rose or set, people could determine the progression of the year and prepare for seasonal changes. This connection between constellations and daily life highlights their importance beyond simple observation. They were not only a way to understand the sky, but also a tool for survival and organization. The stars became a guide for both navigation and timekeeping, linking the movements of the heavens to the rhythms of life on Earth. At the same time, the human tendency to find patterns played a key role in shaping constellations. The brain naturally seeks order in complex information, connecting points into meaningful shapes. When looking at the night sky, this instinct leads us to group stars together, forming patterns that may not exist physically, but feel real to the observer. This ability to recognize patterns allowed early astronomers to simplify the sky. Instead of viewing it as an overwhelming collection of stars, they could break it down into smaller, identifiable sections. These sections became constellations, each with its own name and story, making the sky easier to understand and remember. The process of mapping the sky required careful observation of both bright and faint stars. While the most visible stars define the familiar shapes, many dimmer stars are included within the boundaries of each constellation. These stars help fill in the regions, ensuring that the entire sky is covered without empty spaces. The boundaries themselves do not always follow the shapes we recognize. They are drawn in a way that divides the sky completely, often cutting across star fields in ways that are not visually obvious. This approach prioritizes organization over appearance, creating a system that is useful for mapping rather than purely for storytelling. With this structure in place, astronomers could begin to use smaller patterns within constellations to navigate the sky. These smaller groupings, known as asterisms, often stand out more clearly than the full constellation shapes. They act as guideposts, helping observers locate other stars and constellations more easily. By building from simple patterns to a complete map, the sky becomes a system that can be explored and understood step by step. Each layer of organization adds clarity, turning the vastness of space into something that can be studied and shared. Constellations, though not physically real, provide the framework that makes this possible. As observers continue to study the sky, the consistency of these patterns became increasingly important. Even though the stars themselves are moving slowly through space, the human system of mapping the sky ensures that each region remains identifiable. This stability allows knowledge to be passed from one generation to the next without confusion, preserving both scientific understanding and cultural meaning. In this way, constellations act as a bridge between observation and interpretation. They allow us to take something vast and distant and organize it into a system that can be understood. While the stars themselves exist independently of human thought, the patterns we see among them reflect our need to create order and meaning from what we observe. This balance between reality and perception defines the role of constellations in astronomy. They are not objects that exist in space as connected systems, yet they remain essential tools for navigating and understanding the sky. By continuing to use these patterns, we maintain a connection to both the scientific and cultural history of observing the stars, carrying forward a system that has guided human curiosity for thousands of years. As the idea of constellations became more widely used, the need for a consistent and universal system grew stronger. Early sky watchers created patterns based on their own observations and cultural interpretations, but these patterns were not always agreed upon across different regions. What one group recognized as a particular figure in the sky could appear entirely different to another. This variation made it difficult to share astronomical knowledge in a precise and reliable way. To resolve this, astronomers began working toward a standardized map of the sky. This effort led to a major development in the early 20th century, when the International Astronomical Union established the modern constellation system. In the year 1922, they defined a complete set of 88 constellations that together cover the entire celestial sphere. Each constellation was assigned clearly defined boundaries, similar to borders drawn on a map. These boundaries are not based on the visible shapes formed by the stars, but on a coordinate system that divides the sky into fixed regions. As a result, even areas of the sky that do not form recognizable patterns are still included within a constellation. The purpose of this system is not to preserve only the familiar figures, but to ensure that every part of the sky can be identified and referenced with precision. With this structure in place, every point in the sky belongs to exactly one constellation. There are no gaps between regions and no overlap where a star could belong to more than one. This creates a complete framework that allows astronomers to describe the location of any object in the sky simply by naming its constellation. Whether observing a distant galaxy, a faint nebula, or a single star, this system provides a consistent method of identification. Although the boundaries remain fixed, the stars themselves are constantly in motion. Each star travels through the galaxy over long periods of time, following its own path. This motion, known as proper motion, is extremely slow from our perspective, but over thousands or millions of years, it becomes significant. As stars move, the shapes of constellations gradually change. If observed over very long timescales, the familiar patterns would begin to stretch and distort. Lines that once formed clear shapes would shift, breaking apart into new arrangements. The constellations recognized today would eventually become unrecognizable, replaced by patterns that future observers might interpret differently. This change is gradual, but it reveals that the figures we see in the sky are not permanent. Despite these changes, the constellation boundaries remain stable. The map of the sky stays consistent, even as the stars within it move. This stability allows astronomers to maintain a reliable reference system across generations. Observations made at different times can still be compared accurately because the regions of the sky remain clearly defined. This standardized mapping represents a shift from purely cultural interpretations of the sky to a structured scientific framework. While the shapes of constellations still reflect human imagination, their boundaries now serve a practical function. They provide a system that supports precise observation, communication, and classification of celestial objects. Long before this system was established, constellations were closely tied to mythology and storytelling. Ancient civilizations used the stars to create narratives that explained natural phenomena and preserved cultural beliefs. These stories often involved gods, heroes, and creatures, each placed among the stars as a way of remembering and sharing knowledge. Many of the constellations recognized today have their origins in Greek mythology. Ancient Greek observers identified patterns in the sky and associated them with figures from their stories. These included heroes, animals, and symbols connected to their beliefs. By linking stars to familiar narratives, they created a system that was both memorable and meaningful. Greek constellations, however, were influenced by even earlier traditions. The Babylonians had already begun mapping the sky and assigning meaning to star patterns. Greek astronomers built upon this foundation, adapting and expanding earlier ideas into a more developed system. This process shows how knowledge of the sky evolved through the contributions of multiple cultures over time. Other cultures developed entirely different ways of organizing the same stars. In China, astronomers divided the sky into smaller groupings known as asterisms, each representing elements of their own cultural and philosophical systems. These groupings did not correspond directly to the constellations recognized in Western astronomy, demonstrating that the same stars can be interpreted in many ways. Polynesian navigators also relied on the stars, using familiar patterns to guide their journeys across vast ocean distances. Without written maps or modern instruments, they memorized the positions of stars and their movement across the sky. These patterns allowed them to determine direction and maintain their course, turning the night sky into a reliable navigational system. This diversity of interpretation shows that constellations are not fixed in meaning, but shaped by human perspective. Different cultures observed the same sky and created different systems to understand it. Each interpretation reflects the environment, needs, and beliefs of the people who developed it. The constellations used today represent only one of many possible ways to organize the stars. Beyond storytelling, constellations played an important role in practical life. Ancient societies depended on natural cycles to guide their activities, and the stars provided a consistent way to track time. The appearance and disappearance of certain constellations signaled changes in the seasons, helping people understand when to plant crops or prepare for shifts in weather. This connection between constellations and seasonal change was especially important for agriculture. Farmers observed the night sky to determine the timing of planting and harvesting. When a particular constellation appeared at a certain point in the year, it indicated that conditions were suitable for specific tasks. This allowed communities to coordinate their activities with greater accuracy. Before the development of written calendars, this system provided a reliable method of measuring time. The regular motion of stars across the sky created patterns that could be observed and remembered. By tracking these patterns, people could follow the progression of the year and prepare for seasonal changes. Constellations also became linked to cultural traditions and events. Certain star patterns were associated with specific ceremonies or rituals, marking important moments within a society. The appearance of a constellation could signal the beginning of a festival or the time to perform particular practices. This connection reinforced the role of the sky as a cultural guide. The night sky functioned as a shared reference that connected communities to both time and tradition. By observing the same patterns year after year, knowledge could be passed down through generations. This created a system of understanding that remained stable even without written records. The human tendency to recognize patterns played a central role in the creation of constellations. The mind naturally organizes visual information, connecting points into shapes that can be easily remembered. When looking at the stars, this instinct leads to the formation of patterns that help simplify a complex view. By grouping stars into recognizable forms, early observers transformed the night sky into something more structured. Instead of seeing thousands of individual points of light, they could focus on a smaller number of familiar shapes. These shapes provided reference points that made navigation and communication easier. The process of mapping the sky involved both bright and faint stars. The most visible stars define the outlines of constellations, but dimmer stars fill in the regions between them. This ensures that each constellation forms a complete area rather than just a simple outline. The inclusion of faint stars allows the sky to be divided fully without leaving empty spaces. The boundaries of constellations do not always follow the visible shapes that people recognize. They are drawn to create a complete and organized system, often cutting across star fields in ways that are not immediately obvious. This approach prioritizes structure over appearance, ensuring that every part of the sky is included within a defined region. Through this system, constellations serve as a framework that allows the sky to be organized and understood. They provide a way to divide a vast and complex view into manageable sections, making it possible to study and describe celestial objects with clarity. This framework supports both observation and communication, forming the foundation of how the night sky is mapped. The stars that make up constellations are not physically connected in space, yet they appear to form clear and recognizable patterns when viewed from Earth. This apparent organization is the result of human perception rather than actual proximity. Some of the stars grouped within a single constellation may lie relatively close to us, while others are separated by vast distances, sometimes hundreds or even thousands of light years apart. Despite this, the human mind instinctively connects these distant points of light into shapes that feel meaningful and structured. This tendency to recognize patterns is a fundamental part of how humans interpret the world. When faced with a complex visual field, the brain seeks to simplify it by identifying relationships between individual elements. In the case of the night sky, this leads to the grouping of stars into lines and shapes that can be easily remembered. Early observers did not see isolated stars scattered randomly across the sky. Instead, they saw figures, outlines, and symbols that allowed them to organize what would otherwise be an overwhelming number of points of light. The process of forming constellations begins with the brightest stars, as these are the most visible to the naked eye. These stars act as anchor points, defining the main structure of a pattern. Once these bright stars are identified, additional stars may be included to complete the shape or fill in gaps. Over time, these patterns become familiar, allowing observers to recognize them quickly and use them as reference points. Even though these patterns are not physically real, they serve an important purpose. By turning a complex star field into a set of named shapes, early astronomers created a system that made the sky easier to understand and communicate. Instead of describing the position of a star in isolation, it could be identified as part of a larger pattern. This allowed knowledge of the sky to be shared and passed down through generations. The concept of patterns in the sky also reflects the influence of perspective. From Earth, the stars appear arranged on a flat surface, as if they are part of a dome surrounding the planet. This illusion makes it easier to connect stars into shapes, as their distances are not immediately apparent. In reality, the stars exist in three-dimensional space, scattered throughout the galaxy. The patterns we see are therefore a projection, created by viewing a complex structure from a single point. If the position of the observer were to change, the patterns would change as well. Moving to a different location in space would alter the apparent positions of stars, causing familiar constellations to break apart and reform into new shapes. This shows that constellations are not fixed structures, but visual interpretations that depend on where they are observed from. Despite this, the patterns remain consistent from Earth, allowing them to function as a stable system for observation. The same stars appear in the same relative positions night after night, creating a reliable framework that can be used for navigation and study. This consistency is what makes constellations useful, even though they are not physically connected. As observers became more familiar with these patterns, the need for a more precise system of organization emerged. While the shapes themselves provided a useful guide, they were not sufficient for detailed mapping of the sky. To address this, astronomers developed a method of dividing the celestial sphere into defined regions, creating a structured system that could be used to locate any object in the sky. The celestial sphere is an imaginary sphere that surrounds the Earth, onto which all stars and celestial objects are projected. This concept simplifies the complexity of space by treating the sky as a two-dimensional surface. By imagining the stars as points on this sphere, astronomers can map their positions using a consistent framework. When formalizing constellations within this system, astronomers considered both bright and faint stars. The bright stars define the familiar outlines that people recognize, but the faint stars play an equally important role in defining the boundaries of each region. These dimmer stars fill in the areas between the main patterns, ensuring that the entire sky is covered without gaps. The boundaries of constellations are drawn in a way that divides the celestial sphere completely. These boundaries do not always follow the shapes formed by the stars. Instead, they are based on a coordinate system that allows each region to be clearly defined. As a result, the visible outline of a constellation may extend beyond its official boundary, or that its boundary may include areas where no obvious pattern exists. This approach ensures that every point in the sky belongs to exactly one constellation. No matter where an observer looks, that region of the sky can be identified as part of a specific constellation. This eliminates ambiguity and allows astronomers to describe locations with precision. For example, when observing a faint object through a telescope, it may not be immediately clear which constellation it belongs to based on visible patterns alone. However, by using the established boundaries, its position can be determined accurately. This helps astronomers to catalogue objects and share their findings in a consistent way. The use of faint stars in defining these regions highlights the difference between constellations as visual patterns and constellations as mapped areas. The familiar shapes are only a small part of the larger system. The full extent of a constellation includes many stars that are not easily visible, forming a complete region rather than just an outline. This distinction is important for understanding how constellations are used in modern astronomy. While the shapes provide a helpful way to recognize patterns, the boundaries provide a precise method of mapping. Together, they create a system that is both intuitive and functional. The process of mapping the celestial sphere also required the development of coordinate systems that could describe positions in the sky. These systems allow astronomers to measure the location of stars and other objects relative to fixed reference points. By combining these coordinates with constellation boundaries, the sky can be charted with a high degree of accuracy. This mapping system laid the foundation for star charts. This represents the positions of stars and constellations in a visual format. These charts allow observers to identify constellations and locate specific objects, providing a guide for both amateur stargazers and professional astronomers. As this system developed, it became possible to navigate the sky more effectively. By using constellations as reference points, observers could move from one region to another, locating stars and objects with greater ease. This method of navigation relies on recognizing patterns and understanding their position within the larger map. The combination of pattern recognition and structured mapping creates a powerful system for exploring the sky. The patterns provide a way to identify regions quickly, while the boundaries ensure that each region is clearly defined. This helps observers to move from general recognition to precise identification. In this way, constellations serve both as visual guides and as a framework for organization. They bridge the gap between human perception and scientific measurement, allowing the sky to be understood in both intuitive and analytical terms. The role of patterns in the sky is therefore not limited to simple recognition. It extends into the way we organize and interpret the entire celestial sphere. By connecting stars into shapes, early observers created a foundation that later developed into a structured system for mapping the sky. This system continues to be used today, supporting everything from basic stargazing to advanced astronomical research. The constellations, though not physically real, provide a consistent way to divide and understand the sky. They allow us to take a vast and complex universe and organize it into something that can be explored and studied with clarity. This mapping approach also reinforces how the sky is understood as a continuous surface rather than a collection of isolated points. By assigning every area to a constellation, astronomers ensure that there are no undefined regions. Even areas that appear empty to the naked eye still belong to a specific section of the celestial sphere. This completeness is essential for maintaining consistency when observing and recording objects in the sky. The inclusion of faint stars within constellation boundaries further supports this idea of total coverage. While these stars may not contribute to the familiar shapes, they provide the necessary detail to define each region fully. Without them, the boundaries would be incomplete, and the system would lose its precision. In this way, both visible and less visible stars work together to create a complete and functional map. Another important aspect of mapping the celestial sphere is the ability to compare observations over time. Because the boundaries remain fixed, astronomers can track changes within a specific region without confusion. For example, if a new object is discovered within a constellation, its position can be recorded and shared with confidence that others will be able to locate it using the same reference system. This consistency allows observations to build upon one another, contributing to a growing body of knowledge. The use of constellations as reference regions also simplifies communication. Instead of describing an object using complex coordinates alone, it can be associated with a familiar constellation. This provides an immediate sense of location, even before precise measurements are considered. For observers, this makes the process of finding objects more intuitive, as they can begin with a known pattern and then refine their search within that area. The relationship between visual patterns and mapped regions creates a layered system of understanding. At the surface level, constellations are recognized as shapes formed by bright stars. Beneath that, they function as defined areas that include many additional stars and objects. This layered approach allows both casual observers and experienced astronomers to use the same system in different ways depending on their needs. For those observing the sky without instruments, the patterns provide a way to identify regions quickly. For those using telescopes, the boundaries offer a precise framework for locating objects that may not be visible to the naked eye. This dual function makes constellations a versatile tool, bridging the gap between simple observation and detailed study. As observers become more familiar with the sky, they begin to see how these regions connect. One constellation leads to another, forming a continuous map that spans the entire celestial sphere. This continuity allows for systematic exploration, where each region can be studied in relation to its neighbors. By moving from one constellation to the next, the sky can be navigated in an organized and methodical way. This organization also supports the development of star catalogs, where objects are recorded along with their positions. By noting the constellation in which an object is located, astronomers create a system that is both structured and easy to interpret. This method ensures that information can be shared clearly without ambiguity or confusion. Over time, this structured approach has become essential for astronomy. It allows observations to be compared, verified, and expanded upon, creating a reliable foundation for further study. Without such a system, it would be far more difficult to organize the vast amount of information contained within the night sky. The combination of pattern recognition and structured mapping ultimately defines how constellations are used. The patterns provide an entry point, allowing observers to identify regions of the sky with ease. The boundaries provide precision, ensuring that each region is clearly defined and consistently understood. Together, these elements create a system that transforms the night sky into an organized and accessible framework. Through this system, the sky becomes something that can be explored step by step. Each constellation represents a section of the celestial sphere, and each section contains its own collection of stars and objects. By understanding how these sections are defined and connected, observers gain a clearer sense of how the sky is organized as a whole. This approach does not change the physical nature of the stars, but it changes how they are perceived and studied. By imposing structure on what might otherwise appear random, constellations allow the sky to be understood in a systematic way. This structured understanding forms the basis for everything that follows in the study of astronomy. Within the broader structure of constellations, smaller and often more recognizable patterns begin to stand out. These patterns are known as asterisms, unlike constellations. These are formally defined regions of the sky. Asterisms are informal groupings of stars that create distinct and easily identifiable shapes. They may exist entirely within a single constellation or span across several. Their importance comes from their visibility and simplicity, making them useful reference points for observers. One of the most well-known examples of an asterism is the Big Dipper. This is part of the constellation Ursa Major. This grouping of stars forms a clear and memorable shape, with a bowl and a handle that are easy to recognize. While Ursa Major includes many more stars within its boundaries, the Big Dipper stands out as the most prominent pattern. Because of its clarity, it has been used for centuries as a guide in the night sky. Another example is the line of stars known as Orion's Belt. This asterism consists of 3 bright stars arranged in a straight line, located within the constellation Orion. These stars are highly visible and form one of the easiest patterns to identify. Once located, they serve as a starting point for finding other stars and constellations nearby. This shows how asterisms function as anchors within the larger structure of the sky. The usefulness of asterisms lies in their ability to simplify navigation. While constellations can sometimes be complex or difficult to recognize in full, asterisms provide a clear entry point. Observers can locate a familiar asterism and then use it to orient themselves, gradually identifying surrounding stars and constellations. This step-by-step approach makes the sky more accessible, especially for those learning to observe it. Because asterisms are based on visual patterns rather than formal boundaries, they are more flexible in their definition. Different cultures may recognize different asterisms within the same region of the sky. This reflects the same principle seen with constellations, where human perception shapes how patterns are identified. However, asterisms often focus on the most obvious groupings, making them more universally recognizable despite cultural differences. These patterns also highlight how the brightest stars tend to dominate visual perception. The stars that form asterisms are usually among the most luminous in their region, drawing attention and creating strong visual connections. This helps them to stand out even in conditions where fainter stars may not be visible. As a result, asterisms remain useful in a variety of observing conditions, from dark rural skies to more light-polluted environments. The role of asterisms extends beyond simple recognition. They act as directional tools, helping observers locate key points in the sky. One of the most important uses of an asterism is in finding the North Star. By following the line formed by the outer stars of the Big Dipper's bowl, an observer can trace a path to a single bright star that marks the direction of north. This star, known as Polaris, occupies a special position in the sky. It lies very close to the point directly above Earth's North Pole. Because of this alignment, Polaris appears nearly fixed in place, while other stars seem to rotate around it over the course of the night. This makes it an essential reference point for navigation, as its position indicates true north, regardless of the observer's location in the northern hemisphere. The apparent stillness of Polaris is not due to it being motionless, but rather a result of Earth's rotation. As Earth spins, the sky appears to move in a circular pattern. Stars rise in the east, travel across the sky, and set in the west. However, near the pole, this motion becomes less noticeable. Stars close to Polaris trace small circles, while Polaris itself remains almost stationary at the center of this rotation. This behavior allows Polaris to serve as a reliable guide. By locating it, an observer can determine direction without the need for instruments. This has made it invaluable for navigation throughout history, particularly for travelers and sailors who relied on the stars to guide their journeys. However, the position of the pole star is not fixed over very long periods of time. The Earth itself undergoes a slow and gradual change in orientation known as precession. This motion is similar to the wobble of a spinning top, where the axis of rotation slowly traces a circular path. As Earth's axis shifts, the point in the sky that marks the North Pole changes as well. Over a cycle of approximately 26,000 years, this movement causes different stars to take turns being the pole star. Polaris is currently close to this position, but it will not remain there indefinitely. In the distant future, another star will occupy this role, while Polaris will move away from the central point. One example of this shift involves the star Vega. This will become the pole star in roughly 12,000 years. In the past, other stars have held this position, guiding ancient observers in the same way Polaris does today. This cycle demonstrates that even the most stable reference points in the sky are subject to long-term change. The concept of precession reveals how Earth's motion influences what we see in the sky. While the stars themselves are distant and largely unaffected by Earth's movements, our perspective changes over time. This causes gradual shifts in the alignment between Earth and the stars, altering which stars appear in key positions. Despite this long-term change, the timescale is so vast that it does not affect observations within a human lifetime. Polaris remains a reliable guide for current observers, and its position continues to provide a stable reference point for navigation. However, understanding precession adds another layer to the study of the sky, showing that even seemingly fixed patterns are part of a dynamic system. The relationship between asterisms and pole stars illustrates how simple patterns can lead to deeper understanding. A straightforward grouping of stars can guide an observer to a key reference point. This in turn reveals larger processes such as Earth's rotation and axial movement. This progression from observation to explanation is a central aspect of astronomy. By using asterisms as starting points, observers gain access to a structured way of navigating the sky. These patterns act as stepping stones, leading from familiar shapes to more complex systems. They provide both practical guidance and insight into the underlying mechanics of the celestial sphere. In this way, asterisms serve as both tools and entry points. They simplify the process of identifying regions of the sky while also connecting to broader concepts such as motion, orientation, and long-term change. Through them, the sky becomes not only easier to recognize, but also easier to understand. The usefulness of asterisms becomes even clearer when considering how they function as reliable visual shortcuts within the larger and more complex structure of constellations. While full constellations may require familiarity and practice to recognize in their entirety, asterisms provide immediate recognition. This helps an observer to quickly orient themselves, even if they are not yet comfortable identifying every star within a constellation. By starting with a simple and distinct pattern, the observer can build outward, gradually identifying the surrounding structure with greater confidence. This layered approach to observation reflects how knowledge of the sky develops over time. At first, only the most obvious patterns are recognized. These patterns then become reference points, allowing additional stars and shapes to be identified in relation to them. Over time, this process creates a mental map of the sky, where each asterism connects to a broader network of constellations. This method does not require memorizing the entire sky at once, but instead builds understanding step by step. The consistency of these patterns is essential to their usefulness. Although the stars move across the sky during the night, their relative positions remain fixed. The shapes formed by asterisms do not change from one night to the next, allowing them to serve as dependable guides. This stability is what allows them to be used repeatedly, providing a consistent reference regardless of when or where they are observed within a given region. The connection between asterisms and navigation extends beyond simple direction finding. By identifying a familiar pattern, an observer can estimate their orientation and position. For example, once the Big Dipper is located, it not only points toward Polaris, but also provides a sense of the sky's rotation around the northern point. This awareness of movement adds depth to the observation, linking static patterns to dynamic processes. In addition, the use of asterisms helps reduce the complexity of the sky when observing without instruments. Instead of scanning randomly, the observer can move with intention, using known patterns to guide their search. This reduces uncertainty and makes the process more efficient. It transforms observation, from a passive act into an active and structured exploration. Turning again to the concept of the pole star, its importance becomes even more evident when considered in relation to the wider motion of the sky. As Earth rotates, the stars appear to trace circular paths around the celestial poles. These paths are largest near the horizon and become smaller as they approach the pole. At the center of this motion lies the pole star, marking the axis around which the entire sky appears to turn. This circular motion is a direct result of Earth's rotation. This completes one full cycle in 24 hours. From the perspective of an observer on Earth, this rotation causes the stars to move across the sky in a predictable pattern. The presence of a nearly fixed point at the center of this motion provides a stable reference, making it possible to understand and anticipate the movement of the stars. The concept of precession introduces a slower and less noticeable form of motion, but one that has profound implications over long periods of time. Unlike the daily rotation of Earth, this is easily observed. Precession occurs gradually over thousands of years. It represents a shift in the orientation of Earth's axis, changing the direction in which the axis points. As this shift occurs, the position of the celestial poles changes relative to the stars. As a result, the star closest to the pole also changes over time. Polaris currently occupies this position, but it is only one point along a much larger cycle. In the distant past, other stars served as pole stars, and in the future, new stars will take on this role. This long-term cycle demonstrates that the sky is not static, even if it appears stable within a human lifetime. The patterns we observe are part of a larger system that evolves slowly over time. Understanding precession provides insight into this broader perspective, revealing that even the most familiar features of the sky are subject to change. The relationship between short-term and long-term motion creates a layered understanding of the sky. On one level, the daily rotation provides a predictable and repeatable pattern that can be observed each night. On another level, precession introduces gradual change that becomes apparent only over many generations. Together, these motions illustrate how the sky can be both stable and dynamic at the same time. Asterisms and pole stars work together within this system, connecting immediate observation with long-term processes. A simple pattern such as the Big Dipper can lead to the identification of Polaris. This in turn reveals the axis of Earth's rotation. From there, the concept of precession extends this understanding further, showing how that axis itself changes over time. This progression from simple observation to deeper understanding reflects the way knowledge of the sky develops. It begins with recognizing patterns, continues with identifying reference points, and expands into understanding the movements that shape those patterns. Each step builds upon the previous one, creating a comprehensive view of the celestial sphere. Through this process, the sky becomes more than a collection of stars. It becomes a system that can be explored, understood, and predicted. Asterisms provide the entry points, while concepts such as precession reveal the underlying mechanics. Together, they form a bridge between what is seen and what is understood. The movement of constellations across the sky is one of the most noticeable features of the night. Over the course of a single night, the stars appear to rise in the east, travel across the sky, and set in the west. This motion gives the impression that the entire celestial sphere is rotating around the Earth. In reality, this apparent movement is caused by the rotation of the Earth itself. As the Earth spins on its axis, it completes one full rotation in approximately 24 hours. This rotation causes different parts of the sky to come into view as the night progresses. Stars that were once below the horizon rise into view, while others gradually disappear. This constant motion creates a predictable pattern, allowing observers to anticipate where constellations will appear at different times during the night. The path that stars follow across the sky depends on their position relative to the celestial poles. Stars near the equator of the celestial sphere trace wide arcs, rising and setting in a clear path across the horizon. In contrast, stars closer to the poles follow smaller circular paths, appearing to rotate around a fixed point. This variation in motion adds complexity to the sky, but it also provides useful information about orientation and position. This daily motion creates a sense of rhythm in the night sky. At the beginning of the evening, certain constellations dominate the view. As time passes, these constellations move westward, making way for new patterns to rise in the east. By observing this progression, it becomes possible to estimate the passage of time during the night. In addition to this nightly motion, the sky also changes over the course of the year. This seasonal variation is caused by the Earth's orbit around the Sun. As the Earth travels along its path, the night side of the planet faces different regions of space at different times of the year. As a result, the constellations visible in the sky change gradually from season to season. During one part of the year, a particular group of constellations may be visible in the evening sky. Several months later, those same constellations may no longer be visible at night, as they appear in the daytime sky instead. This shift occurs because the Earth has moved to a different position in its orbit, changing the direction in which the night side faces. For example, a constellation that is prominent in winter may not be visible at all during the summer months. As the Earth continues its orbit, that constellation will eventually return to the night sky, completing a yearly cycle. This repeating pattern allows constellations to be associated with specific seasons. The relationship between constellations and the seasons has long been used as a method of tracking time. By observing which constellations are visible at certain times of the year, people can determine the progression of the seasons. This system is based on the predictable nature of Earth's motion. This ensures that the same patterns repeat year after year. Some constellations, however, do not follow the usual pattern of rising and setting. These are known as circumpolar constellations. They are located close to the celestial poles and remain above the horizon throughout the entire night. Instead of rising and setting, they appear to circle around the pole star in a continuous loop. The presence of circumpolar constellations depends on the observer's location on Earth. In regions closer to the poles, more constellations remain visible throughout the night. In contrast, observers closer to the equator see fewer circumpolar constellations as more of the sky rises and sets each night. This introduces the importance of latitude in determining which constellations are visible. The position of an observer on Earth has a direct impact on the portion of the sky that can be seen. Different latitudes provide different views of the celestial sphere, meaning that not all constellations are visible from every location. Observers in the northern hemisphere have access to constellations that are centered around the northern celestial pole. These include circumpolar constellations that never set below the horizon. At the same time, many southern constellations remain permanently out of view, hidden below the horizon. In contrast, observers in the southern hemisphere see a different portion of the sky. They have access to constellations near the southern celestial pole, many of which are never visible from northern locations. This creates two distinct views of the sky, each shaped by the observer's position on Earth. For those located near the equator, the situation is different. From this position, a larger portion of the sky is visible over the course of a year. Many constellations from both the northern and southern hemispheres can be seen at different times, as they rise and set throughout the seasons. This makes equatorial regions unique in their ability to access a wide range of constellations. The limitations imposed by latitude explain why early astronomers were only familiar with certain parts of the sky. Civilizations located in the northern hemisphere developed systems based on the constellations they could observe. Southern constellations remained unknown to them, simply because they were never visible from their location. It was not until exploration expanded into the southern hemisphere that new constellations were identified and mapped. During the 17th century, European explorers traveled to regions where the southern sky could be observed. Astronomers accompanying these journeys began documenting previously unseen constellations, adding them to the growing map of the sky. These newly identified constellations were often named differently from the older, mythological ones. Instead of being associated with gods and heroes, many were named after scientific instruments or concepts. This reflects a shift in perspective, where the focus moved from storytelling to observation and measurement. The addition of these constellations completed the mapping of the celestial sphere, ensuring that both northern and southern regions were fully represented. This expansion allowed the constellation system to become truly global, accommodating observations from all parts of the Earth. The influence of latitude also affects how constellations appear in the sky. As an observer moves from one hemisphere to another, familiar patterns can appear rotated or inverted. A constellation that appears upright in one hemisphere may seem upside down in another. This change in orientation can make recognition more challenging for those unfamiliar with the new perspective. Despite this, the relative positions of the stars within a constellation remain unchanged. The pattern itself is the same, even if its orientation appears different. This consistency allows observers to adapt, learning to recognize constellations from different viewpoints. The need to adjust to these changes highlights the role of perspective in observing the sky. Constellations are not fixed images, but patterns that can appear differently depending on the observer's position. Understanding this helps to reinforce the idea that constellations are interpretations shaped by both location and perception. The combination of daily motion, seasonal change, and variation by latitude creates a dynamic view of the sky. Constellations are not static features, but part of a system that is constantly shifting. These changes are predictable, allowing observers to learn and anticipate the movement of the stars. By understanding these patterns, the sky becomes a structured and reliable system. The movement of constellations provides information about time, direction, and location, linking the motions of the Earth to the patterns observed in the sky. This connection forms the basis for navigation, timekeeping, and the continued study of the celestial sphere. The predictability of these movements is what allows the sky to function as a dependable system. Each night, the same patterns repeat, with stars rising and setting in consistent positions relative to the horizon. Over longer periods, the seasonal changes follow a regular cycle, returning the same constellations to the same parts of the sky at the same time each year. This consistency creates a framework that can be learned and relied upon, turning observation into understanding. By recognizing how constellations shift throughout the night, an observer can estimate both direction and time without the need for instruments. The position of a constellation relative to the horizon can indicate how much time has passed since it first appeared. As the stars continue their movement, this progression provides a natural measure of time, similar to the movement of a clock. The seasonal changes extend this concept further, linking the sky to the passage of the year. As different constellations appear at different times, they mark the transition from one season to another. This connection between the sky and the seasons is not arbitrary, but a direct result of Earth's orbit and the changing angle from which the night sky is viewed. Latitude adds another layer to this system, shaping how these patterns are experienced in different parts of the world. Observers at higher latitudes see a sky that rotates more tightly around the pole, with a greater number of circumpolar constellations remaining visible throughout the night. In contrast, observers closer to the equator experience a sky where more stars rise and set, creating a broader range of visible constellations over time. This variation means that no single view of the sky is complete. Each location offers a different perspective, revealing some constellations while hiding others. To understand the full structure of the celestial sphere, observations from multiple latitudes must be considered together. This shows the importance of exploration in expanding knowledge of the sky. The discovery of new constellations in the southern hemisphere reflects this process. As observers traveled beyond the regions where earlier constellations had been defined, they encountered new patterns that had never been recorded. These additions extended the existing system, ensuring that the entire sky could be mapped and understood. At the same time, the introduction of new constellations demonstrates how the system continues to evolve. While the modern set of constellations is now fixed, the process that created them was shaped by observation, exploration, and the need to organize new information. This historical development shows that the constellation system is both a product of its time and a tool that adapts to expanding knowledge. The combined effects of daily rotation, seasonal change, and variation by latitude create a complete picture of how the sky behaves. Each factor contributes to the overall movement and appearance of constellations, linking the observer's position on Earth to the patterns seen above. By understanding these relationships, the sky becomes a system that can be interpreted with clarity and consistency. Along a specific path in the sky lies a group of constellations that have been given particular importance throughout human history. This path is known as the ecliptic. This represents the apparent motion of the sun across the sky over the course of a year. As the Earth orbits the sun appears to move against the background of stars, passing through a series of constellations that form a band across the celestial sphere. These constellations are known as the zodiac. Traditionally, 12 constellations are associated with this path, forming the basis of the zodiac signs used in astrology. However, when examined from an astronomical perspective, the Sun actually passes through 13 constellations along the ecliptic. The constellation Ophiuchus lies along this path, but is often excluded from the traditional zodiac system. This difference highlights an important distinction between astronomy and astrology. Astronomy is concerned with the actual positions and movements of celestial objects, while astrology is based on symbolic interpretations that do not always align with physical reality. The zodiac signs used in astrology divide the sky into 12 equal sections, regardless of the true size or boundaries of the constellations. In contrast, the constellations themselves vary in size and shape. Some cover large areas of the sky, while others are relatively small. As a result, the Sun spends different amounts of time in each constellation, rather than moving through them in equal intervals. The division of the zodiac into 12 equal parts is therefore a simplified system that does not reflect the true structure of the sky. Because of this, the position of the Sun in the sky does not always match the zodiac sign assigned by astrology. A person identified as being born under one sign may find that, according to astronomical observation, the Sun was actually located in a different constellation at the time of their birth. This difference arises from the way the zodiac system has been defined and maintained over time. The reason for this mismatch becomes clearer when considering the long-term movement of the Earth's axis. As described earlier, the Earth undergoes a slow shift in its orientation, known as precession. This movement causes the position of the equinoxes to change gradually over time, shifting the alignment between the Earth and the constellations. When the zodiac system was first established, the positions of the constellations and the divisions of the zodiac were more closely aligned. However, as precession has continued over thousands of years, this alignment has shifted. The Sun now appears in different constellations at the same points in the year compared to where it appeared in ancient times. This shift amounts to roughly one zodiac sign over a period of about 2,000 years. As a result, the dates associated with each zodiac sign in astrology no longer correspond to the actual positions of the constellations. The system has remained fixed in its original form, while the sky itself has gradually changed. From an astronomical perspective, the constellations remain the reference points for mapping the sky. Their boundaries, as defined by modern systems, provide a stable framework for identifying the location of celestial objects. This approach prioritizes accuracy and consistency, ensuring that observations can be compared and shared reliably. Astrology, on the other hand, continues to use the traditional zodiac system, maintaining the original divisions regardless of the changes caused by precession. This creates a symbolic framework that is separate from the physical structure of the sky. While it retains cultural significance, it does not reflect the actual positions of the stars and constellations. The distinction between these two approaches underscores the importance of understanding how constellations are used in different contexts. In astronomy, they serve as a precise system for organizing and locating objects in the sky. In astrology, they function as part of a symbolic system that interprets celestial patterns in relation to human experience. The ecliptic itself remains an important reference in both systems. It represents the plane of Earth's orbit and defines the path along which the Sun, Moon, and planets appear to move. This shared path creates a connection between the movements of these objects and the constellations they pass through. Observing the Sun's position relative to the constellations provides insight into the structure of the solar system. The apparent motion of the Sun is a reflection of Earth's orbit, linking the daily experience of sunrise and sunset to the larger motion of the planet around the Sun. This connection reinforces the idea that the patterns seen in the sky are influenced by the movements of Earth itself. The concept of the zodiac also demonstrates how early attempts to organize the sky were influenced by both observation and interpretation. While the constellations along the ecliptic are real regions of the sky, the division into 12 equal signs represents a simplification that made the system easier to use and understand. Over time, this simplified system became widely adopted, shaping how many people think about the relationship between the Sun and the stars. However, modern astronomy has moved beyond this framework, relying instead on the precise boundaries of constellations to map the sky accurately. The effect of precession continues to influence this relationship, gradually altering the alignment between Earth and the constellations. Although the change is slow, it accumulates over time, shifting the positions of celestial objects relative to the calendar. This ongoing movement highlights the dynamic nature of the sky, even within systems that appear stable. The use of constellations as fixed regions allows astronomers to account for these changes while maintaining a consistent framework. By separating the concept of constellations from symbolic interpretations, astronomy preserves a system that reflects the actual structure and movement of the sky. Through this understanding, the zodiac becomes an example of how human interpretation interacts with observation. It shows how systems created to explain the sky can evolve differently depending on their purpose, whether practical, scientific, or cultural. The constellations remain the underlying structure, providing a reliable map against which these interpretations can be measured. The continuing shift caused by precession also affects how the equinoxes align with the constellations. The equinoxes are points in Earth's orbit where day and night are of equal length, and they were once used as reference markers for dividing the zodiac. Over time, as precession alters the orientation of Earth's axis, these reference points slowly move relative to the background of stars. This gradual shift changes the relationship between the calendar and the constellations, further separating the symbolic zodiac from the astronomical one. This movement is not noticeable within a single lifetime, but over many generations it becomes clear that the alignment has changed. Ancient astronomers recorded the positions of the Sun and constellations with careful observation, and when those records are compared to modern measurements, the difference becomes evident. This long-term drift shows that even systems designed to track the sky must account for the slow but continuous changes in Earth's orientation. The ability to measure and understand this shift has been important in refining how the sky is mapped. By recognizing that precession affects the apparent positions of celestial objects, astronomers have been able to adjust their systems to maintain accuracy. This ensures that observations remain consistent, even as the underlying alignment between Earth and the stars continues to change. In practical terms, the use of fixed constellation boundaries allows astronomers to avoid confusion caused by this drift. Instead of relying on shifting reference points, such as the equinoxes, they use the stable regions of the sky defined by constellations. This approach keeps the system grounded in observable positions rather than symbolic divisions, making it more reliable for scientific study. The difference between symbolic systems and mapped regions becomes especially important when tracking objects over time. A star, planet, or galaxy may be observed at different points across many years, and its position needs to be recorded in a way that remains meaningful. By referencing constellations, astronomers ensure that these positions can be compared accurately, regardless of changes caused by precession. This distinction reinforces the role of constellations as a practical framework rather than a symbolic one. While the zodiac remains part of cultural tradition, the constellation system provides a consistent method for organizing and understanding the sky. It allows observations to be recorded with precision, supporting both current study and future comparison. At the same time, the continued use of the zodiac in popular culture shows how historical systems can persist even when their original alignment has shifted. The symbolic meanings attached to zodiac signs remain unchanged, even though the positions of the constellations have moved. This separation between meaning and measurement highlights the different purposes these systems serve. The interplay between these approaches reflects a broader theme in the study of the sky. Human understanding often begins with observation and interpretation, creating systems that are meaningful and useful. As knowledge expands, these systems are refined, separating symbolic ideas from measurable reality. The constellation system represents this refinement, providing a structure that is based on observation and maintained through careful definition. The path of the ecliptic continues to serve as a guide for understanding the motion of the sun, moon, and planets. These objects follow a similar path across the sky because they lie within the same plane of the solar system. By observing their movement against the background of constellations, astronomers can track their positions and understand their motion relative to Earth. This relationship between moving objects and fixed constellations creates a dynamic view of the sky. The constellations form a stable background, while the sun, moon, and planets move across it in predictable patterns. This contrast allows observers to distinguish between different types of motion, identifying which changes are caused by Earth's movement and which are due to the movement of other objects. Over long periods, this system provides a reliable way to chart the sky and understand its changes. The constellations remain as fixed reference regions, while the positions of moving objects are recorded relative to them. This method ensures that the sky can be studied as both a stable framework and a system of ongoing motion. As the system of constellations became more refined and widely adopted, their role expanded beyond simple pattern recognition and storytelling. Constellations began to serve a more practical and essential function in astronomy, acting as a structured way to organize and locate objects in the sky. Rather than being seen only as shapes, they became reference regions that could be used to identify the position of stars, galaxies, and other celestial objects. In this context, constellations function much like an addressing system. Just as locations on Earth are described using regions, cities, and streets, objects in the sky can be identified by the constellation in which they appear. This provides an immediate sense of location, allowing astronomers to communicate clearly and efficiently about where something can be found. For example, when an astronomer refers to the Andromeda galaxy, the name itself indicates that the object is located within the region of the sky defined by the constellation Andromeda. This does not mean that the galaxy is physically connected to the stars of that constellation. In reality, it lies far beyond them, at a distance of millions of light years. However, by associating it with a specific constellation, its position can be easily understood and communicated. This method of naming extends to many other objects in the sky. The Orion Nebula, for instance, is located within the constellation Orion. Again, the nebula is not physically part of the constellation, but its position within that region makes it easier to identify. By using constellation names as part of object names, astronomers create a system that links each object to a specific area of the sky. This approach simplifies the process of locating objects. Instead of searching the entire sky, an observer can narrow their focus to a particular constellation. Once within that region, more precise methods can be used to find the exact position of the object. This layered approach makes observation more efficient and reduces the complexity of navigating the sky. The idea of constellations as address labels also supports the organization of astronomical data. Large catalogues of stars and other objects often include the constellation name as part of their classification. This helps data to be sorted and grouped by region, making it easier to manage and access information. By dividing the sky into clearly defined areas, constellations provide a framework that supports both observation and record keeping. In addition to simplifying communication, this system ensures consistency across different observers and locations. Because the boundaries of constellations are fixed, the same object will always be associated with the same region of the sky. This eliminates ambiguity and allows observations to be shared and compared without confusion. The use of constellations as a grid over the sky further enhances this system. The celestial sphere can be thought of as divided into a network of regions, each corresponding to a constellation. This grid provides a reference framework that allows any point in the sky to be identified and described. It transforms the sky from an unstructured view into an organized system that can be navigated with precision. Telescopes and other observing instruments often rely on this framework when targeting specific objects. By identifying the constellation in which an object is located, observers can direct their instruments to the correct region before making finer adjustments. This process depends on the consistency of the constellation system. This ensures that each region remains clearly defined. The concept of constellations as a grid also supports the development of coordinate systems that provide even greater precision. While constellation names indicate general location, coordinates can specify exact positions within those regions. Together, these systems create a complete method for mapping and navigating the sky. The importance of this system becomes even more apparent when considering the vast number of objects that exist in the universe. Without a structured way to organize these objects, it would be extremely difficult to keep track of observations or share information effectively. Constellations provide the foundation for this organization, allowing astronomers to categorize and locate objects within a consistent framework. This method of organization is not limited to professional astronomy. Amateur observers also benefit from using constellations as reference points. By learning to identify constellations, they gain access to a system that allows them to explore the sky more effectively. Once a constellation is recognized, it becomes easier to locate other objects within that region. The use of constellations as address labels reflects a shift from viewing the sky as a collection of patterns to understanding it as a structured system. While the patterns remain useful for recognition, the boundaries and regions provide a practical way to organize information. This dual function allows constellations to serve both as visual guides and as tools for precise observation. The consistency of this system is what makes it so effective. Because the boundaries do not change, the same reference points can be used over time. This helps observations made in the past to remain relevant, as they can be compared with new observations using the same framework. This continuity is essential for building a long-term understanding of the sky. As astronomical knowledge has expanded, the number of known objects has grown significantly. From stars and planets to galaxies and nebulae, the sky contains a vast range of phenomena. The constellation system provides a way to organize this complexity, ensuring that each object can be placed within a defined region. In effect, constellations act as a bridge between the vastness of the universe and the need for human understanding. They reduce the scale of the sky to manageable sections, allowing observers to focus on one region at a time. This approach makes it possible to study the universe in a systematic and organized way. The idea of using constellations as addresses also highlights the importance of standardization. Without agreed boundaries and naming conventions, it would be difficult to ensure that different observers are referring to the same location. The modern constellation system solves this problem by providing a shared framework that is recognized worldwide. Through this system, the sky becomes a mapped and navigable space. Each constellation represents a defined area, and each area can be explored in detail. By using these regions as reference points, astronomers can locate objects, record observations, and share information with clarity. The concept of constellations as address labels therefore extends far beyond their original role as patterns in the sky. It transforms them into a fundamental part of how the universe is studied and understood. By providing a structured way to organize the sky, constellations make it possible to navigate and explore a space that would otherwise be overwhelming. The effectiveness of constellations as an addressing system becomes even more apparent when considering how they are used in large-scale observation and research. Modern astronomy involves the study of vast numbers of celestial objects, many of which are too faint to be seen without specialized instruments. In order to manage this volume of information, a clear and consistent framework is required. Constellations provide this framework by dividing the sky into regions that can be systematically studied. When astronomers survey the sky, they often focus on one region at a time, using constellation boundaries to organize their work. This helps observations to be grouped and compared within a defined area. By working within these regions, patterns and relationships between objects can be identified more easily, supporting a deeper understanding of the structure of the universe. The use of constellations also simplifies the process of recording and retrieving data. Observational records often include the constellation in which an object is located, along with more precise positional information. This makes it possible to organize large datasets in a way that is both logical and accessible. When researchers refer to a particular object, the constellation name provides an immediate reference point, reducing the need for lengthy descriptions. In addition to supporting data organization, this system aids in communication between observers. Astronomy is a collaborative field, with researchers around the world sharing information and building on each other's work. A standardized method of identifying locations in the sky ensures that this communication is clear and accurate. When a constellation name is used, it provides a common reference that is understood regardless of language or location. This shared framework is particularly important when coordinating observations across different instruments and observatories. Telescopes located in different parts of the world may observe the same region of the sky at different times. By using constellation boundaries as a reference, these observations can be aligned and compared, contributing to a more complete understanding of the observed objects. The concept of constellations as a grid also supports the development of automated systems for observing the sky. Modern telescopes can be programmed to scan specific regions, using constellation boundaries as part of their targeting system. This helps large areas of the sky to be surveyed efficiently, with data collected in a structured and organized manner. The reliability of this system depends on the stability of the constellation boundaries. Because these boundaries are fixed, they provide a consistent reference that does not change over time. This ensures that observations remain valid and comparable, even as new data is collected and analyzed. The constellations act as a permanent framework within which the dynamic processes of the universe can be studied. For observers using telescopes, the process of locating objects often begins with identifying the relevant constellation. Once this region is found, the observer can use more precise methods to pinpoint the object's exact position. This step-by-step approach combines general recognition with detailed measurement, making it easier to navigate the sky at different levels of detail. The addressing function of constellations also extends to educational contexts, where they provide a way to introduce the structure of the sky. By learning the constellations, students and observers gain an understanding of how the sky is organized. This knowledge forms the basis for further exploration, allowing more complex concepts to be built upon a familiar framework. Through this system, the sky becomes more than a visual experience. It becomes a structured environment that can be explored, recorded, and understood. Constellations provide the foundation for this structure, turning a vast and seemingly unorganized field of stars into a system that can be navigated with clarity. The combination of naming, mapping, and organization transforms constellations into a practical tool for astronomy. They are no longer simply patterns that represent stories or figures, but essential components of a system that supports observation and discovery. By assigning each object to a specific region, the sky is divided into manageable sections, allowing knowledge to be built and shared effectively. This system continues to be used as new discoveries are made. As more objects are identified and studied, they are placed within the existing framework of constellations. This ensures that the organization of the sky remains consistent, even as our understanding of it expands. The constellations provide a stable structure that supports ongoing exploration and research. Across the night sky, there is a band of light that stretches from one horizon to the other, forming a dense and luminous pathway through many constellations. This band is known as the Milky Way, and it represents the combined light of countless stars within our own galaxy. To the unaided eye, it appears as a soft glow, broken into brighter and darker regions that vary in intensity across the sky. The Milky Way passes through multiple constellations, often making their patterns more difficult to distinguish. In areas where the density of stars is high, the familiar outlines of constellations can become less clear as the background glow blends with the brighter stars that define the shapes. This creates a more complex visual field where the contrast between individual stars and the surrounding light is reduced. In addition to the brightness of the Milky Way, there are also regions where the light appears to be interrupted. These darker areas are not empty space, but are caused by clouds of interstellar dust that block the light from stars behind them. These dust clouds create visible gaps within the band of the Milky Way, forming patterns that stand out against the surrounding brightness. These dark regions are known as dark nebulae, and they play an important role in shaping how the Milky Way appears from Earth. Instead of a uniform glow, the galaxy is seen as a combination of bright and dark structures, with the dust clouds creating contrast that highlights the complexity of the system. This variation adds depth to the sky, revealing that what appears to be a simple band of light is actually a layered and intricate structure. In constellations that lie along the Milky Way, these dark nebulae can partially obscure the familiar star patterns. The outlines of constellations may appear broken or incomplete, as sections of the sky are hidden behind these clouds. This makes it more challenging to trace the intended shapes, requiring observers to look more carefully to identify the underlying pattern. Despite this, the presence of the Milky Way also enhances the richness of the sky. The increased number of stars within these regions provides a sense of depth and scale, making the sky appear more densely populated. This contrast between dense star fields and dark gaps creates a visual complexity that goes beyond the simple outlines of constellations. Ancient observers were aware of these dark regions and incorporated them into their understanding of the sky. Rather than focusing only on the bright stars, some cultures began to recognize shapes formed by the absence of light. These patterns, defined by dark clouds rather than bright stars, offered an alternative way of interpreting the sky. One of the most notable examples of this approach comes from the Inca civilization. This identified figures within the dark regions of the Milky Way. Instead of connecting bright stars to form shapes, they observed the dark patches and saw animals and figures within them. These included shapes resembling a llama, a fox, and other creatures, each defined by the contrast between light and shadow. This method of identifying constellations demonstrates that patterns in the sky are not limited to visible stars. The absence of light can be just as meaningful as its presence, creating shapes that are equally recognizable. This expands the concept of constellations beyond simple star groupings, showing that the sky can be interpreted in multiple ways. The recognition of dark constellations also reflects the role of perception in shaping how the sky is understood. Different cultures focused on different aspects of the sky, choosing to emphasize either the bright stars or the dark spaces between them. Both approaches create patterns, but they highlight different features of the same environment. This contrast between light and dark patterns reveals a deeper complexity in how the sky is observed. The Milky Way is not just a backdrop for constellations, but an active part of the visual system that influences how patterns are perceived. Its brightness can obscure certain shapes, while its dark regions can create entirely new ones. The interaction between these elements creates a layered experience of the sky. On one level, constellations are formed by connecting bright stars. On another level, the Milky Way introduces additional structure, both through its dense star fields and its dark nebulae. Together, these elements create a dynamic and textured view of the night sky. For observers, this means that recognizing constellations within the Milky Way requires a different approach. The usual method of connecting bright stars may need to be adjusted, taking into account the surrounding brightness and the presence of dark regions. This adds complexity to observation, but also provides a richer and more detailed view. The presence of dark constellations also highlights how cultural interpretation can vary based on observation. While some traditions focus on the brightest and most obvious features, others explore subtler patterns that emerge from contrast and absence. This diversity of interpretation reinforces the idea that constellations are shaped by perception as much as by observation. At the same time, the Milky Way provides a broader context for understanding the position of our solar system within the galaxy. The band of light represents the plane of the galaxy, where the majority of its stars are located. By observing this band, it becomes possible to gain a sense of the structure of the galaxy and our place within it. This connection between local observation and larger structure adds another layer to the study of constellations. While constellations divide the sky into regions, the Milky Way reveals the larger system in which those regions exist. It provides a background that connects individual patterns to the overall structure of the galaxy. The combination of bright constellations and dark nebulae creates a complex visual system that reflects both physical structure and human interpretation. The stars provide points of light that can be connected into shapes, while the dust clouds create areas of contrast that form alternative patterns. Together, they demonstrate the multiple ways in which the sky can be organized and understood. The visibility of the Milky Way also depends on observing conditions. This can influence how clearly both bright and dark patterns are seen. In areas with very little artificial light, the band of the Milky Way becomes far more pronounced, revealing intricate detail within its structure. The contrast between bright star clouds and dark nebulae becomes sharper, allowing the eye to distinguish patterns that might otherwise remain hidden. In such conditions, the sky appears deeper and more layered, making both traditional constellations and dark constellations easier to identify. In contrast, in locations with significant light pollution, much of this detail is lost. The faint glow of the Milky Way can become difficult to see, and the dark regions that define many of the shadow-based patterns may disappear entirely. This changes the way the sky is perceived, reducing it to only the brightest stars and the simplest constellations. As a result, the richness of the Milky Way and the subtle patterns it contains are closely tied to the conditions under which it is observed. Even when the Milky Way is clearly visible, its position in the sky changes throughout the year, just as constellations do. At certain times, the band stretches high overhead, making it easier to observe its full structure. At other times, it may lie closer to the horizon, where atmospheric effects can reduce clarity. This variation adds another layer of movement to the sky, linking the appearance of the Milky Way to the same seasonal cycles that affect constellations. The interaction between the Milky Way and constellations also influences how observers learn to navigate the sky. In regions where the galaxy is prominent, the usual patterns of constellations may appear partially blended into the background. This requires a more careful approach, where observers rely not only on the brightest stars, but also on their relative positions within the surrounding glow. Over time, this builds a more detailed understanding of how constellations are situated within the larger structure of the galaxy. Dark constellations, in particular, depend on this contrast to remain visible. Without the surrounding brightness of the Milky Way, the shapes formed by dark nebulae would not stand out. Their visibility relies on the balance between light and shadow, where the absence of starlight becomes a defining feature. This makes them unique among sky patterns, as they are defined not by what is seen, but by what is hidden. The recognition of these dark patterns demonstrates that the sky can be interpreted in more than one way at the same time. Bright constellations and dark constellations coexist, each offering a different perspective on the same region of space. One highlights the presence of stars, while the other reveals the structure of the material between them. Together, they provide a more complete view of the galaxy and the processes within it. This dual interpretation also reinforces the idea that constellations are not fixed in meaning. Just as different cultures identified different patterns among the stars, they also chose to focus on different aspects of the sky. Some traditions emphasized brightness and connection, while others focused on contrast and absence. Both approaches create valid and meaningful systems, shaped by observation and interpretation. The Milky Way, with its combination of light and shadow, serves as a reminder that the sky is not a uniform field, but a complex environment with layers of structure. The constellations that lie within it are influenced by this complexity, appearing differently depending on their position relative to the galaxy. Some constellations are defined clearly against darker regions of the sky, while others are embedded within dense star fields, requiring more effort to distinguish. This variation encourages a deeper level of observation, where the sky is not simply recognized, but studied. By paying attention to both the bright and dark features, observers gain a more detailed understanding of the celestial sphere. This understanding extends beyond individual constellations, revealing how they fit within the broader structure of the galaxy. The view of the night sky is not the same from every location on Earth. The constellations that can be seen, their position in the sky, and the way they appear all depend on where the observer is located. One of the most significant differences occurs between the northern and southern hemispheres, where entirely different regions of the sky become visible. Observers in the northern hemisphere see a sky centered around the northern celestial pole. This region includes constellations that remain visible throughout the year, circling around the pole without ever setting below the horizon. These constellations provide a stable reference forming patterns that can be seen on any clear night. At the same time, a large portion of the southern sky remains permanently out of view, hidden below the horizon. In contrast, observers in the southern hemisphere experience a different arrangement. Their sky is centered around the southern celestial pole. This lies in a region that does not contain a bright star equivalent to Polaris. Instead of a single clear marker, the southern sky relies on patterns of stars to identify direction. Constellations near the southern pole circle around this point, remaining visible throughout the night in a similar way to their northern counterparts. Because of this difference, many constellations are unique to one hemisphere or the other. Constellations that are well known in the northern hemisphere, such as those near the northern pole, cannot be seen from southern locations. Similarly, constellations that lie near the southern pole are not visible from the north. This creates two distinct sets of constellations, each associated with a different half of the Earth. The division between these views is not absolute, but gradual. As an observer moves closer to the equator, more of the sky becomes visible. From equatorial regions, a larger portion of both the northern and southern skies can be seen over the course of a year. Constellations that are hidden from higher latitudes may rise above the horizon for part of the year, expanding the range of observable patterns. This variation highlights the importance of location in determining what can be seen. The sky is not a fixed image, but a view that changes depending on the observer's position. As a result, knowledge of constellations is often shaped by geography, with different regions of the world developing familiarity with different parts of the sky. The appearance of constellations also changes depending on the observer's location. As one moves from the northern hemisphere to the southern hemisphere, familiar constellations can appear rotated or even inverted. A pattern that appears upright in one hemisphere may seem upside down in the other. This change in orientation can make recognition more difficult at first, even though the relative positions of the stars remain the same. This inversion occurs because the observer's perspective has changed. When looking at the sky from opposite sides of the Earth, the same region is viewed from a different angle. The stars themselves have not moved, but the way they are seen has changed. This reinforces the idea that constellations are patterns shaped by perspective rather than fixed images. Adapting to a new view of the sky requires a shift in how patterns are recognized. Observers must learn to identify constellations based on the arrangement of stars rather than their orientation. Over time, this becomes easier, as the underlying structure of the pattern remains consistent, even when it appears rotated. This process of adaptation reflects a broader principle in observing the sky. The constellations provide a framework, but the observer must adjust to their specific viewpoint. By understanding how perspective influences appearance, it becomes possible to recognize patterns under different conditions. Orientation in the sky is closely linked to understanding direction. In the northern hemisphere, the presence of Polaris provides a clear reference point for north. In the southern hemisphere, where no bright pole star is present, other methods are used. One common approach involves using the Southern Cross, a prominent constellation that can be used to approximate the direction of the southern celestial pole. By extending an imaginary line along the longer axis of the Southern Cross, observers can estimate the location of the pole. This method provides a practical way to determine direction, even in the absence of a bright guiding star. It demonstrates how constellations can be used not only for recognition, but also for orientation and navigation. The ability to use constellations for direction depends on understanding their position relative to the horizon. As the Earth rotates, the apparent movement of stars provides clues about direction and time. By observing how constellations rise, set, and move across the sky, it becomes possible to build a mental map that connects patterns to orientation. This mental mapping is an important part of learning to navigate the sky. It involves recognizing patterns, understanding their movement, and relating them to fixed points, such as the celestial poles. Over time, this creates a sense of familiarity, where the sky becomes an organized and predictable system. The differences between northern and southern skies also illustrate how the constellation system was developed over time. Early astronomers were limited to the sky visible from their location, leading to a focus on specific regions. As exploration expanded, new constellations were identified and added to the system, creating a more complete map of the sky. This expansion required adaptation, as observers encountered patterns that were unfamiliar. The introduction of new constellations reflected the need to describe regions of the sky that had not been previously recorded. This process highlights how the constellation system grew through observation and exploration, rather than being created all at once. The variation in sky views also affects how constellations are learned and remembered. Observers tend to become familiar with the patterns that are most visible from their location. This familiarity shapes their understanding of the sky, influencing which constellations are recognized first and how they are used as reference points. At the same time, the underlying structure of the celestial sphere remains consistent. The same stars exist regardless of location, and their positions relative to one another do not change. What changes is the portion of the sky that is visible and the angle from which it is observed. This consistency allows knowledge to be shared, even when the experience of the sky differs. The need to adapt to different views reinforces the importance of understanding the sky as a system rather than a fixed image. Constellations are part of this system, providing a framework that can be applied from any location. By learning how this framework works, observers can adjust their perspective and recognize patterns under a variety of conditions. The combination of geographic variation and consistent structure creates a balance between difference and stability. The sky appears different depending on where it is observed, but the system used to describe it remains the same. This helps the constellation system to function as a universal framework, capable of accommodating multiple perspectives. Through this framework, the sky becomes a space that can be navigated and understood from any location on Earth. The constellations provide reference points, while the observer's position determines how those points are seen. By combining these elements, it becomes possible to interpret the sky in a way that is both consistent and adaptable. The process of adapting to different views of the sky also deepens an observer's overall understanding of how constellations function as a system. When the same constellation is seen from different latitudes, its path across the sky changes, rising at different angles and reaching different heights above the horizon. This variation provides additional insight into how the celestial sphere is oriented relative to the Earth. As observers become more familiar with these changes, they begin to recognize that constellations are not fixed in position, but part of a larger system of motion and perspective. The way a constellation appears is shaped not only by the arrangement of its stars, but also by the observer's location and the time of observation. This reinforces the idea that constellations are a framework for understanding the sky rather than static images. The ability to adjust to these differences is an important part of developing skill in observing the sky. It requires moving beyond simple recognition and towards a deeper awareness of how patterns behave under different conditions. By understanding how constellations shift with latitude and orientation, observers gain a more flexible and complete view of the celestial sphere. This flexibility is especially important when considering travel between different regions of the world. An observer moving from one hemisphere to another must learn to reinterpret familiar patterns while also becoming acquainted with entirely new ones. This process highlights both the consistency and the diversity of the sky, showing how a single system can present multiple perspectives. At the same time, the use of constellations as reference points ensures that this adaptation remains grounded in a consistent framework. Even when patterns appear rotated or partially hidden, their position within the constellation system remains the same. This helps observers to connect new experiences with existing knowledge, building a more comprehensive understanding of the sky. The relationship between orientation and movement also becomes clearer through this process. By observing how constellations rise, arc across the sky, and set, it becomes possible to visualize the rotation of the Earth more directly. This connection between observation and motion helps to reinforce the underlying mechanics of the celestial sphere, linking what is seen to the physical processes that create it. In this way, the differences between northern and southern skies are not simply variations in appearance, but opportunities to understand the structure of the sky more deeply. Each perspective reveals different aspects of the same system, contributing to a more complete and unified view. Through observation, adaptation, and comparison, the sky becomes a coherent whole, shaped by both its physical properties and the position of the observer. The constellations that divide the sky are not equal in size. Some cover vast regions that stretch across large portions of the celestial sphere, while others occupy much smaller areas that contain only a handful of visible stars. This variation in size reflects how the constellation system developed over time, shaped by observation, cultural influence, and later by formal standardization. Large constellations can span wide areas of the sky, containing numerous stars, and often extending across regions that include both bright and faint objects. These constellations may take longer to recognize in full, as their patterns are spread out and less immediately obvious. In contrast, smaller constellations are more compact, with tighter groupings of stars that can be identified more quickly. Despite their size, both large and small constellations serve the same purpose within the system, acting as defined regions that contribute to the complete mapping of the sky. The differences in size do not affect how constellations function as part of the celestial framework. Each one represents a specific area, regardless of how many stars it contains or how large it appears. This ensures that the entire sky is divided into regions that can be referenced consistently, even if those regions vary greatly in scale. Some of the largest constellations stretch across areas where the density of stars is relatively low, making their boundaries less obvious to the eye. Others lie within regions of the Milky Way, where the density of stars is high, creating a more complex and detailed appearance. This contrast shows that the size of a constellation does not necessarily correspond to how visually prominent it is. The process of defining these constellations involved balancing visual recognition with the need for complete coverage. Early observers focused on the most noticeable patterns, but as the system became more formalized, it was necessary to include all areas of the sky. This led to the creation of constellations that may not correspond to clear visual shapes, but still serve an important role in dividing the celestial sphere. The variation in size also highlights the difference between constellations as patterns and constellations as mapped regions. The patterns are based on visible stars, while the regions include everything within their boundaries. As a result, a large constellation may contain vast areas where no obvious pattern exists, while a small constellation may appear more clearly defined. In modern astronomy, the importance of constellations lies not in their shapes, but in their role as part of a structured system. They provide a way to organize the sky into manageable sections, allowing objects to be located, studied, and recorded with precision. This system supports both observation and communication, ensuring that information about the sky can be shared accurately. The development of modern sky maps builds upon this system, combining the traditional constellation framework with precise measurements and detailed observations. These maps represent the positions of stars, constellations, and other celestial objects, providing a visual guide that reflects both the structure of the sky and the data collected through observation. Modern sky maps are based on coordinate systems that allow the position of any object to be described with accuracy. These coordinates work alongside constellation boundaries, providing both general and precise methods of locating objects. While the constellation indicates the region, the coordinates specify the exact position within that region. This combination of systems allows for a high level of detail in mapping the sky. Astronomers can identify objects with precision, track their movement, and compare observations over time. The constellations provide the framework, while the coordinates provide the detail, creating a complete system for understanding the sky. At the same time, the use of sky maps continues to rely on the human ability to recognize patterns. Even with advanced instruments and digital tools, the constellations remain an important part of how the sky is visualized. They provide a familiar structure that connects modern observation with the long history of studying the stars. The role of imagination in this system has not disappeared. While constellations are now defined by precise boundaries, their origins as patterns created by human perception remain an essential part of their identity. The shapes that were once imagined in the stars continue to influence how they are recognized and remembered. This connection between imagination and structure creates a unique balance within the constellation system. On one hand, it is a scientific framework used for precise observation. On the other, it is a reflection of human creativity, shaped by the desire to find meaning in the patterns of the sky. This balance allows the system to function both as a practical tool and as a cultural expression, Even as technology advances, the constellations remain a central part of how the sky is understood. Digital sky maps and automated telescopes still rely on the same framework, using constellation boundaries to organize observations and guide exploration. This continuity shows that the system is both adaptable and enduring, capable of supporting new methods of study while maintaining its original structure. The ability to map the sky with precision does not remove the sense of wonder that comes from observing it. Instead, it adds depth to that experience, revealing the complexity behind the patterns that are seen. The constellations provide a way to connect this complexity to something familiar, allowing the sky to be both understood and appreciated. The variation in size, the structure of the mapping system, and the role of imagination all contribute to a complete understanding of constellations. They are not simply patterns or regions, but part of a system that brings together observation, organization, and interpretation. Through this system, the sky becomes a space that can be explored with clarity and meaning. As this understanding develops, the constellations remain as a constant reference, linking past observations with present knowledge. They provide a framework that supports both scientific study and personal exploration, allowing the sky to be approached in a way that is both structured and intuitive. The way constellations vary in size also affects how observers interact with different regions of the sky. Larger constellations often require a broader view to fully recognize, encouraging observers to take in wider sections of the sky at once. This can create a more expansive sense of space, where patterns are spread out and require time to trace. In contrast, smaller constellations can be identified more quickly, offering clear and concentrated patterns that stand out within a limited area. This difference influences how observers build familiarity with the sky. Larger constellations may be learned gradually, with individual sections becoming recognizable before the full pattern is understood. Smaller constellations, by comparison, can often be recognized as a complete shape more immediately. Over time, both types contribute to a layered understanding, where the sky is seen as a combination of broad regions and detailed patterns. The variation in size also reflects how the constellation system balances completeness with usability. To divide the entire sky into regions, it was necessary to include areas that do not form obvious shapes. Some constellations therefore exist primarily as mapped regions rather than easily recognizable figures. These regions may contain faint stars or sparse groupings, yet they remain essential for maintaining a complete and continuous framework. In modern sky maps, this framework becomes more apparent. The boundaries of constellations are clearly defined, often outlined in a way that shows how the sky is divided into adjoining sections. These maps reveal that the familiar shapes represent only a small part of each constellation, while the full region extends beyond what is immediately visible to the eye. The use of detailed sky maps allows observers to move beyond simple recognition and into precise identification. By following the boundaries and using coordinate systems, it becomes possible to locate objects that are not visible without magnification. This adds another level of depth to observation, where the constellations serve as a starting point for exploring more distant and less visible features. Modern mapping tools also allow the sky to be represented in ways that were not possible in the past. Digital maps can display large numbers of stars and objects, adjusting the level of detail depending on the needs of the observer. Despite these advancements, the underlying structure remains the same. The constellations continue to provide the framework that supports this detail, ensuring that even the most advanced systems are grounded in the same organizational principles. The continued use of constellations in these tools highlights their adaptability. While the methods of observation have evolved, the basic system of dividing the sky into regions has remained effective. This consistency allows new technology to build upon existing knowledge, rather than replacing it entirely. At the same time, imagination still plays a role in how constellations are perceived. Even with precise boundaries and detailed maps, the human tendency to see patterns remains. Observers continue to recognize shapes, connect stars, and interpret what they see in personal ways. As a result, constellations exist both as defined regions and as visual experiences shaped by perception. The balance between structure and imagination allows the constellation system to remain both functional and meaningful. It provides a way to organize the sky while still allowing room for individual interpretation. This dual role connects modern astronomy with its historical origins, where observation and imagination work together to create the first patterns in the sky. The presence of both large and small constellations also encourages exploration across different scales. Some regions invite broad observation, where the focus is on the overall pattern and its position in the sky. Others invite closer attention, where smaller groupings and finer details become the focus. This range of scales adds variety to observation, making the sky a space that can be explored in different ways. Through this system, the sky becomes a structured yet open environment. The constellations provide the framework, defining regions and supporting precise mapping. Within that framework, the observer brings their own perception, recognizing patterns and building familiarity over time. This combination creates a complete experience where the sky is both organized and interpreted. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about constellations.